Okay, so in this lesson, what we're going to be doing is we're going to take a look at and see how do three planes intersect. Okay, now we are talking about three distinct planes because if they're not distinct, then some of them could be the same. We're back to two planes, or we even have one plane. We've already talked about, how two planes can intersect, right? We did that in the last lesson. So all of the techniques that we're going to be showing in each of the five scenarios. Okay, so there's going to be five scenarios in here. We've already done all the techniques. We've done the strategy. We know the process. Okay, so what I'm going to do is I'm going to explain all of this. I've got some different pictures here to help us understand and visualize what's going on. What you could do, which is a good idea, in your OneNote section, I've included this part, a second lesson today, which is called the student copy. All right. And it's identical words. All right. That what I have or what I'm going to be using, except there's big spaces here for you to go ahead and do the algebra as well. All right. I'm not going to go through the algebra. All right. I'll talk about it all, but I think it's a good idea to for you to go through it and to verify, you know what's going on. You can pause the video at any time, do the work, and then listen to the explanation. Okay. If you're having some difficulties, if not, just keep going and go through it all. Okay. So anyway, that's my suggestion to you. So with these, all right, we're going to start. As I said, there are five different situations that you could have with three distinct planes. All right. The first thing, and I'll show you here on the side, is if you look at the pink and the light green and the purple here, those are planes shown on the edge. These are parallel planes. So you can have three parallel planes. All right. And what you would note about these three parallel planes, maybe the black won't show up. All right, this green would probably show up better, is that for each of these, you're going to have a normal vector, okay, on each. Since the planes are parallel, each of these vectors are scalar multiples of each other, okay? Now, you notice for them to be distinct, the planes aren't the same. The full planes, the d value of the planes will not be scalar multiples of each other. All right. The normal vectors will. The planes or the d values will not have that same relationship. So if you take a look, okay, again, the word part says the same thing. If we look at the solution or the example that we have, I'm going to go back to black here. All right, so for this example, if we're going to show that pi 1, pi 2, and pi 3 are parallel and distinct, all right, find out what the normals are. All right, are they scalar multiples of each other? You'll see that they are. And then you show that the d values don't have the same scalar multiple as the just the normals. Okay, so you see, for example, -3 n1 is equal to n3, but -3 pi 1 is not pi 3. So those two are distinct from each other. All right. Then you look at the next two, the relationship between n1 and n2, and pi 1, pi 2 don't have the same relationship. Okay, three distinct planes. All right, so the next case, we have two parallel planes and one that's not, that cuts through. So what do we have in there? If we take a look at it, what geometrically forms, all right, you can see with these three planes, what geometrically forms is that you have two parallel lines. Okay, see you've got a line right there and there's another line that comes right there. They're parallel because they lie on the two parallel planes. Okay, so that's geometrically what could form. All right, what's the condition for that? Well, if you take a look again at the normal vectors, okay, you're going to have a normal vector coming off of this one, which is a scalar multiple of this normal vector, all right? But the third normal vector is not a scalar multiple of the other two, okay? So you see it's similar to the one above, but you've got this third one that's not a scalar multiple, all right? So the idea here. So how do you prove the second? Take a look at it, all right? All right. Here's the example. We've got a pi 1, pi 2, and a pi 4. So I switched one up, all right, because we already know pi 1 and pi 2 are parallel to each other. Okay, this should be the same from above. All right. Pi 4, right? The normal vector is not a scalar multiple of the other two, so they will form these parallel lines. Now, again, the question could be in the textbook, find the equation of these lines, right? And again, if you go back to the diagram here, basically how you find it is you just take a look at the strategy we did in the previous lesson to find the line of intersection for two of the vectors or two of the planes. I think this one would be pi 1, this one would be pi 4, okay? And then to find the other, you would have the intersection, the same strategy between pi 2 and pi 4. All right. So you can try your hand at those, refresh your memory on that strategy. Okay. So you've got three parallel planes, two parallel planes, and one cut across it. All right. And the next one is an example, let's say in the third example here, you can see we've got three planes that basically form, we call three parallel lines. All right. If you take a look, kind of this triangular shape. All right. I think I still have a pi 1 or whatever, but we've got, the three different planes. Pi 1, I'll just call them pi 2, pi 3. All right. Between pi 1 and pi 3, you can see this line of intersection. Again, how you find it? Same way as we've done in the past, right? Pi 2 and pi 3, there's that line. Okay. And then finally, we've got pi 1 and pi 2 and this line of intersection right there. Okay. So what forms geometrically in this case is three parallel lines. Okay. These lines will never intersect. Okay. So you have three sets of parallel or three parallel lines. All right. How do we show? Again, if we take a look, and I'd like this example here, if you look at the, here's, let's say this is pi 5, right? And we've got a pi 1 here. This one would then be pi 4. So we've got it on its edge. You see the triangle, you look at it. How do you show that this is true? Okay, that we have this case. Again, you look at the normal vectors. You can see that all three of them are coplanar. All right, all three of them are coplanar, and then that means that you can have a linear combination of these three. All right, they're not scalar multiples of each other, right? That was the other part of it. Okay, none of them are collinear, so that you can create some sort of scalar multiple between the normals. All right, now the next part of this is, since you can form the scalar multiple, okay, for example, I've got that here. To have this case, you don't have the same scalar multiple or linear combination, rather, with the planes. The d values wouldn't work the same way. All right. If, for example, I had pi 1 is equal to, sorry, not pi 1, but n1. If you came up with n1 is equal to 2n4 minus 3n5, okay, d1 does not equal the 2 times d4 minus 3 times d5. Okay, the linear combination would not work with the with the planes, the full planes themselves. And that gives you your third case. Okay, take a look. You can go through this example here, show that you do come up with a linear combination with the normals, but you cannot come up with the same linear combination using the d values of the full planes. Okay, so that's what you have. Three parallel lines, you kind of have this triangular prism being formed. All right. Now, if we look, so we're on this note, if we look at the three cases, there is not one point in common with all three planes. Okay, these first three cases are said to be inconsistent. All right, there is no solution, like in the literal sense of what we mean by solution, right? One point that is on all three equations, all three planes. We haven't had that yet. All right, we get that with the very next two. Okay, examples. For example, in this fourth case, we're going to intersect in a common line. All right, all three planes intersect in one common line. Take a look at it here. Okay, this is the idea. This is the case that we were kind of alluding to in the end of the last lesson, right? We have a line of intersection between two, and we can come up with a third plane or an infinite number of planes that have the exact same line of intersection. Okay, that was the last example that we did in the last lesson. All right, but if you take a look at here, okay, in this example, right, we have a couple of things going on. All right, let me change the colors a little bit here. The normal vectors. We can draw out the normal vectors on each of these on the same plane. The normal vectors are coplanar. Okay, the first four cases that we're talking about, this one included, right? All of the normal vectors are coplanar. We can draw them on the same plane. Okay, now we get this line of intersection between the planes. Okay, see, here's the condition. The plane, the difference between example 3 that we just did in this case 4 that we're doing now is that if the normal vectors, let's just say we've got, again, if the normal vectors can be written with a linear combination, so can the planes in the exact same, in the linear combination we have. So you deal with the normals and you can deal with the d values. All right. Now, in order to show this, okay, we use a technique that we've done in the past, right? Finding the linear combination between normals, and then you can check it with the d values. Okay, that's what we do. All right. How do we find the line of intersection? Well, the line of intersection, if we know that there's a line of intersection, and if we can show this, we know there's a line of intersection, then all we do is we just find the line of intersection between two of the planes. That's it. Okay? That'll work. So, you can take a look at this one. All right, show yourself and prove that, yes, in fact, all these planes, all right, do have a linear combination. All right. Now, I talked about this note. In all above 4 cases, the normal vectors and planes have been coplanar. All right. The last example is when these normal vectors are not coplanar. Okay, and they're not coplanar. Well, how do we show that things are not coplanar? We use the scalar triple. Okay, right off the bat, if you want to look at these, right? Do the scalar triple. If it equals 0, they're coplanar. If it doesn't equal 0, They're not coplanar. Boom. What do we have in this example? We get 1 point of intersection, one unique point for all 3 planes. Okay. Here's the example, right? With these 3 planes here, let's say we have a plane 1, we have plane 2. I know that one's a little bit harder to see, but between plane 1 and plane 2, you see that there is this line of intersection, right? That line of intersection intersects with plane 3 at a unique point. Okay, see how it hits there? You can use this line of intersection to come up with the same point because it goes through pi 2. Or you could come up with this line of intersection to hit that unique point because it goes through pi 1. All right. So how do we show that we have this case? Use the scalar triple. Okay, use the scalar triple. When you're eyeballing the normal vectors, okay, you got 3 normal vectors. You're going to look at them and think to yourself, is there a scalar multiple between any of these 2? Oh, I can't see the scalar multiple. Okay. Do they line on the same plane, right? If there's no scalar multiple, you've already reduced your cases down. It's not scalar, it's not case 1, it's not case 2, right? So it could be 3, 4, or 5. So you do the scalar triple. The scalar triple doesn't equal 0. It's case 5. You have 1 point of intersection. That's it. Okay. How do you find the point of intersection? Number 1, find the line of intersection first between any 2, right? So we know how to do that between 2 planes, right? Express one component in terms of the other 2. Sorry, express 2 components in terms of 1, right? Remember the let x be our parameter, right? We use elimination. Get rid of the x, solve for, or sorry, get rid of the y, solve for the z. Get rid of the z, solve for the y, right? And everything will be terms of this x. Then you have your line of intersection. From the line of intersection, you find the intersection between the line and the plane, your third plane, right? Substitute the parametric equations of the line into the plane, and you'll find out what your parameter is to find that unique point. All right, let's take a look at that example there. Show that these intersect at one unique point, pi 1, pi 2, pi 3, and then find that point. So again, start off by using, actually I said start off by inspections, right? By eyeballing these 3. None of these are parallel to each other, meaning we can't find a scalar multiple between n1, n2, and n3, right? So then you can do the scalar triple. Performing the scalar triple shows that you do not get a negative, or a 0 rather. That means they're not coplanar, so they have to intersect at one point. So again, look at the process, right? We have the 3 equations. We're going to, in this case, isolate the x and the z, the z and the y in terms of the x. So then we have our parametric equations of the line of intersection. This is the line of intersection right there. You substitute these parametric equations, the x, y, z, into the third equation, the third plane, and it tells us that the t value is equal to 0. So we can say, okay, fine, we put the t back in and we get into our 3 or our triple okay, our ordered triple. We get our point of intersection, okay? That's the idea. That's what we're doing today, okay? Finding out what case do we have. You're going to have a system of 3 planes. Find the solution. Is there a solution, right? You've got 5 cases, right? 5 cases. 3 parallel lines or 3 parallel planes, 2 parallel planes, right? No parallel. You got this triangle. You have 3 parallel lines, right? None of these have a solution. No solution. There is not one point of intersection between the 3 planes. This one line of intersection. We have a solution, right? One line of intersection, one point of intersection, solution, right? Scalar triple. For these, you're looking at the scalar triple, right? For the first 2, we're eyeballing it. I'll put inspection. The inspection of the normal vectors, right? You can't see a scalar multiple, go to the scalar triple, right? If the scalar triple is 0, then you're either in case 3 or case 4. How do you distinguish between case 3 and case 4? You find the scalar or the linear combination with the normals. It's either going to work with the d values or it's not going to work with the d values, right? Case 3, case 4. If the scalar triple is not 0, you have case 5. All right, one point of intersection you can solve. So with these questions here, all right, I stated here in 8, it says our way. The textbook is going to ask you to do something in terms of what we do with matrices. We are not getting into any matrices in this course, so we don't need to do this. It's kind of like row reduced echelon, elementary, row reduction, things like that. Don't worry about any of that. Just find the answer, the way that we just discussed. Okay, so try out these. Let me know if you have any questions, and good luck.